So my name is Olivier Renault. Good morning, everyone. I am Chief Scientist at the Department of Metrology and Physical Characterization at Leti, CEA, next door. And I will be talking about new capabilities that we recently acquired early this year. And it is about lab-scale hard X-ray photoelectron spectroscopy, HAXPES. So I will be starting by introducing you give you an introduction regarding the platform for nanocharacterization of CEA, because actually CEA-Leti is part of this platform. So at PFNC, basically 3 institutes of CEA Grenoble are sharing their instrument for characterization, and also the staff scientists, who are about 80 people working there. We host about 50 world-class equipments within 3,000 square meter laboratories. And as I was telling you, it is basically 3 institutes working together in different fields of analysis, of materials analysis, called the Centers of Competencies. And one of these Center of Competencies, one of these team, is a team I am more particularly leading, and this is related to surface analysis using photoelectrons, and with some extension towards ion beam analysis, so-called TOF-SIMS. So now a short introduction regarding photoelectron spectroscopy, just to prepare ground for this talk. So photoelectron spectroscopy is a photon in, electron out technique. This is based on the photoelectric effect. So basically you shine your sample with X-rays, or you can also shine your samples with UV photons. And we can go the highest energy that we can use in practice is in the kilo electron voltron, so up to 10 kiloelectron volt, I would say. You have the fundamental relationship, so between the photon energy h nu, the initial energy of the photoelectron in the material, which is the binding energy EB, and the kinetic energy of the electrons, because the electrons are ejected out of the sample, and the spectrometer is measuring kinetic energy. So once you know the kinetic energy, which is measured, you know the photon energy, you can deduce the binding energy, which tells you about the element present at the surface. And from this relation, you see immediately that higher photon energies will produce faster, will generate faster photoelectron, and this is very important for the following. So besides elemental analysis, you can do also, and this is a very key advantage of the technique, you can also have chemical fingerprinting through the core level chemical shift. You have an example below. You can very easily, within the probe volume, discriminate different kind of bonding states for a particular element. So now let's explain why hard X-rays are very useful in photoelectron spectroscopy. We are talking about, as I was mentioning, we are talking about photon energies below 10 keV, typically, so relatively soft X-rays. Originally, this technique was developed at synchrotron facilities, but since 2 or 3 years, I would say, commercial lab-scale instruments are entering the game. So why is HAXPES so interesting? So you increase the excitation energy, so you generate faster electrons, which means that the mean free path of the electrons within the material will increase, and the probing depth will increase. So effectively, the crucial aspect of HAXPES compared to conventional photoelectron spectroscopy is that you increase dramatically the inelastic mean free path, typically by a factor of 3, 4. And this gives you access to the subsurface properties of the material. So you still have synchrotron beamline operating HAXPES end stations, and you have actually one at the SRF. This is a Spanish beamlines plane. But as I was mentioning, and this is the title, the topic of my talk today, recently lab-scale instruments operating with hard X-ray tubes are entering the game. So HAXPES is particularly useful for analyzing buried interfaces in device technology. Indeed, now subsurface of materials are accessible through this technique. In device technology, you have so-called critical buried interfaces. Basically, in many examples, in many devices, the operation of those devices is governed at the nanoscale by interfaces, which are critical because they are quite delicate. And of course, if you want to analyze those critical interfaces, you don't want to destroy them. So this critical point of the interface in device technology was early recognized by Herbert Krömer with this famous statement, the interface is the device. So this is still true today. And you immediately understand that getting access to a subsurface of materials, you can easily, in a non-destructive way, analyze by photoelectron spectroscopy those critical interfaces in device. So now I think my next slide is more about the instrument we've started to implement at PFNC. It is an instrument commercialized by Ulvac-Phi, which is a Japanese-American company. The instrument is called the Quantes, and it provides two X-ray irradiation, the conventional irradiation generated by aluminum alpha target, and the hard X-ray source provided by a chromium target at 5.4 kilo-electron volts. So we have effectively two confocal X-ray microsources with smallest X-ray spot in the range of, say, 7-15 micron. You have a picture of the instrument as it is currently installed at CEA Grenoble next door. It has not a look of a research instrument, but it is very, very efficient. The key thing of the X-ray irradiation technology is that regarding silicon-based systems, we are not losing any sensitivity. When you irradiate with hard X-ray a material and you try to extract photoelectrons, the process can be, as the photon energy is increasing, the process can be quite inefficient. And the key thing here with chromium is that you are not losing sensitivity because you have access to another line or core line of silicon. So I would like to carry on with some application cases, and the first application case is regarding depth profiling. You have now access to to deeper core level lines within the atom because you are exciting with other X-rays, and this gives you the possibility to do non-destructive variable probing depth analysis, because each line at a particular mean free path. So let's take the example of this oxidized titanium nitride material. We can have access to two core level lines, titanium 2P and titanium 1S. Titanium 2P has a low binding energy, which means a high kinetic energy, which means a high mean free path. This is the opposite for titanium 1S, so the K shell of titanium. very high binding energy, which means very low kinetic energy excited by chromium, and therefore, consequently, a very low inelastic mean-free path. When the mean-free path is very low, you have a very high surface sensitivity. This is the reason why on the titanium 1s spectrum, you have only the contribution of you have mostly the contribution of the surface oxide. When you look at the titanium 2p spectrum, you see immediately that the contribution of the bulk, the unoxidized nitride, is very much enhanced. Conversely, the contribution of the surface oxide is drastically decreased. So by analyzing two different kind of X-ray core level lines, you can perform this non-destructive depth profile, so to speak. The second application case is about getting access to more accessible core lines. This is an example of a stack of nitride materials. On the right, you have the aluminum K alpha, so conventional XPS spectrum. And on this spectrum, you see that you have overlapping lines. For example, gallium lines overlap with silicon lines, which makes impossible a proper analysis of this sample. Switching to RD excitation with a chromium source, you get access, as you can see very easily, you get access to deeper core lines of silicon and aluminum, silicon 1s, aluminum 1s, which are very well separated. And immediately you see that with HAXPES, you can have a decent, so to speak, analysis of this sample, which was previously not possible using conventional XPS. The next application case is about buried interfaces in a resistive memory device. I was mentioning the critical interfaces that needs to be controlled in device technology. So I provide you here with an example of such a prototypical memory device. So here we are interested in the interface between the active oxide, hafnium oxide material and the top electrode formed by a combination of titanium film and platinum film. You have the HAXPES general spectrum showing you that the platinum core line is most prominent, but you can have access to the hafnium 3D core line, which provides you with an enhanced sensitivity. So the ionization section of this line is dramatically enhanced. This is about 13 kilobarn at 5 kilo electron volt. And this is to be compared to the another core line, the 4F level, which is used traditionally in XPS, but which has a very much smaller ionization cross section, meaning that the signal will be drastically decreased. So for this example, we use the hafnium 3D core level, which enables you to properly analyze the critical interface between hafnium oxide and titanium. The last application case is about inelastic background analysis. So you have two kinds of features in a photoelectron spectrum. You have the primary photoelectron peaks. These are the peaks I have been talking about until now. But you also have energy losses to lower kinetic energies, and which provide you with an increased probing depth. With core levels, elastic peaks, you have a probing depth which is typically 3 times the mean free path, and using energy losses, you can increase this probing depth up to 8 times the mean free path. So this inelastic background contains information regarding the depth distribution of the element you are interested in, and I provide I'm showing you here an example with buried tantalum below a fairly thick layer of aluminum, either 40 or 60 nanometer of aluminum. So you see on the tantalum spectrum acquired at Synchrotron Spring 8 in Japan that actually the elastic peak displayed with the blue arrow is no longer visible because the tantalum is heavily buried. However, you have a very strong signal of the energy losses electrons, which you can analyze through a particular methodology. And you can reconstruct basically the depth distribution of tantalum. This is what we have been doing in this experiment. So the nominal burying depth is between 40 and 45, and we determined through this method a burying depth between 38 and 44 nanometers, so with a very high accuracy. So you understand that with inelastic background, you can get access to very large probing depths in photoelectron spectroscopy. And we wanted to reproduce this experiment with our new lab scale instrument. In the case of a nitride, of a stack of different nitride materials. So here we are considering aluminum nitride, gallium nitride, and silicon nitride. We are analyzing jointly the silicon 1s line and the gallium 2s2p lines excited with our chromium source. And we can actually evidence some kind of gallium diffusion, upwards gallium diffusion in those stacks, which are intended for power devices. And this gallium diffusion was actually also characterized using cross-sectional TEM. So the message here is that no longer you don't no longer need cross-sectional TEM to perform the analysis. You can use photoelectron spectroscopy and the energy loss analysis. This provides you with a result in a much faster way. I am done with my talk. Just a few words of conclusion. So to mention that RDX-ray photoelectron spectroscopy is now getting into the laboratory. The spectrometer is very versatile. It is actually the same spectrometer, the big brother of a spectrometer, of a commercial spectrometer installed at ST Microelectronics. So we can have a common sample pattern. We can do collaborative work very easily. This spectrometer offers probing depths up to 30 nanometers and up to 80 nanometers thanks to inelastic background analysis. HAXPES is expected to become a standard tool for characterizing subsurface phenomena in materials, and in device technology, buried interfaces are being analyzed non-destructively. Synchrotron excitation will still remain useful for high energy resolution needs. So thanks a lot for your attention, and I'm ready for questions.